Hello everyone and welcome back. Today we talk about comparing different types of functions. I just want to highlight that project 4 is due next class, so you're going to be looking for a date next to class 15. That's when project 4 is due, and at that same moment project 5 will be assigned, due about a week later. So let's take a look at the class notes. Number 1, we start this section by looking at rational functions. Here's an example of one. Ian signs up for a cell phone plan costing $30 per month plus 10 cents per minute. Suppose Ian talks for X minutes in a month. Find a function that represents his A, total cost for the month, B, cost per minute. Pause the video and see if you can fill in those two blanks. Okay, so here are our two functions, 30 plus 0.1x for the total cost, and then if we want the cost per minute, we just take the total cost we just found and divide by x, which is the number of minutes. I think that economists usually put a bar over the thing if they want it to represent an average, so we'll call that C bar for the cost per minute. Number 2, use the formula from above to try to figure out what happens to the cost per minute as the number of minutes becomes A, very large, B, very close to 0. So pause the video and try to get those two answers for the cost per minute function, the C bar function, and come back when you're done. Okay, so hopefully you had some success here, but if x becomes very large, and so I'm going to write this using our standard limit notation. Limit as x goes to infinity. If x becomes very large, then we're going to plug into the C bar function. And we're going to decide what happens. Okay, so if x is really big, then this 0.1x is going to be really big, and adding 30 to that enormous number will have essentially no effect. So I'm going to cross that 30 off temporarily, since it's pretty insignificant when x is big, and what I have left is 0.1x divided by x, and we can cancel those x's and just get 0.1. So in the long run, average cost approaches 0.1. It will never quite get there. It'll always be slightly more than 0.1, but it will get very, very close to 0.1. Part B, what happens when the number of minutes becomes very close to 0? So I'll use the same notation. Here x goes to 0. In this case, I'm going to put a little plus sign here. That means approaching 0 from the right. It doesn't make sense to say that we talked for negative number of minutes. You don't need to worry about putting that plus sign there, but that will indicate that we're coming from above 0, from bigger than 0. Okay, so in this case, if you plug in x equals 0, you'll get, well, this part here will be 0, so I can pretty much ignore that, but you're dividing by 0, which we're told not to do. Okay, well, we're not technically plugging 0 in, just numbers near 0. So if you take 30, so again, we're ignoring this part. So if you take 30 and divide it by numbers that are closer and closer to 0, maybe you'll have like 30 divided by 0.1, and then maybe 30 divided by 0.01, and 30 divided by 0.001. Okay, so that number right there, I think, is 30,000. And hopefully you see that these numbers get bigger and bigger and bigger the closer the x gets to 0. So bigger and bigger, we can symbolize with the infinity. Number 3, without using your calculator, try to come up with a rough sketch of the average cost function based on your answers to the previous question. Pause the video and come back when you think you've got a good sketch. Okay, so for this one, it says as x approaches infinity, the limit is 0.1. So that means that we can draw a horizontal asymptote at 0.1. So it'll be clear x is down there and C bar, the average cost function, is there. And at 0.1, we'll kind of exaggerate it and put it right there. We know that the graph is going to approach that thing. And I'd mentioned it's going to approach it from above. It'll always be a little bigger than 0.1. So we're going to be decreasing and then getting closer and closer to 0.1, never actually getting there. And then the second thing in purple here says that when you approach 0, the average cost goes to infinity. So that means as the x's go this way, the average cost goes this way. So I'm just going to draw something that goes up like that. So here's the rest of this graph. So getting very, very close to the C-bar axis, the vertical axis, but never touching it. Okay, and then it says we can take a look at a GSP file. Let's just go ahead and make a Geogebra file from scratch for this one to confirm. So I'm going to fix the font size and make that a little bit bigger, make it easy to see. Click on this guy and then drag in the open space. Right-click in the blank space to turn on the grid. Okay, so the function that I want to type in here is C of x equals, so just what we had before, 30 plus 0.1x, and that's divided by x. And that looks an awful lot like the graph that we drew. If I click on the axis, I can then rescale, and I can see that it's getting closer and closer and closer to the vertical axis. But even here, I can see there's a tiny space in between, so it never actually touches. This yellow arrow will put me back. Okay, that's good. And then if I drag this way, well, we said we were going to be approaching 0.1. So even though it looks like it's getting closer and closer to the horizontal axis, the x-axis, it actually is getting closer and closer to 0.1. So maybe it would help if we actually, well, you can see it right here. You can see y equals 0.1, and that graph is asymptoting at 0.1. It's not getting down here to 0, it's actually getting to 0.1. And so if I drag this more, you'll see it getting closer and closer and closer to 0.1. That's pretty compelling that it's not going to get below it. Number 4, let's write the cost per minute function as the sum of two other functions and analyze what those two other functions represent. Okay, so I'll put the C-bar function here again. This is copied from above. And we know that we can split this up into two fractions. This is really 30 divided by x plus 0.1x divided by x. So that's just a fact about adding fractions. And then I'll cancel the x's in the second part. So it's 30 over x plus 0.1. Okay, so the average cost per minute is represented by this thing. All right, the 0.1 is the cost per minute that was given, it's 10 cents a minute. What is the 30? Well, the $30 was the fixed cost of having the cell phone in the first place, and then it gets divided into x equal pieces. So this other part right here, this 30 over x, is the fixed cost, and then it's kind of spread out. I guess I'll say it's spread out evenly among the x minutes. So the bigger the x, the more you talk, the more that $30 is getting spread out, the more pieces it's getting spread into, which is why the whole function approached 0.1, because this 30 over x became closer and closer to 0 the more and more you talked. Number 5, a rational function is a ratio of two polynomials. That word ratio is italicized. I will highlight it and just point out that it is in the beginning of the word rational. Is the cost per minute function a rational function? How about the total cost function? Okay, so is cost per minute a rational function? Is it a ratio, meaning a division, of one polynomial divided by another? Well, let's see, the top thing is 30 plus 0.1x, that's a polynomial. X in the bottom, that's a polynomial, so yes, it is a rational function. What about the total cost function? So the total cost function was just the 30 plus 0.1x. If I really need it to be a fraction, there is one thing I can put downstairs that won't change the fraction, and that's a 1. The top thing is indeed a polynomial, and 1, no matter how simple it is also a polynomial. So yes, the total cost function is also a polynomial, is also a rational function. Number 6, which of the following are rational functions? Pause the video here and see if you can figure out exactly which ones are and which ones are not. Remember again, rational function is just a ratio of two polynomials. Okay, part A, x to the 4th minus 1 over x squared plus 1. It's a polynomial divided by another polynomial. Yes, indeed, that is a rational function. 3x to the negative 4, well, can we write it as a ratio, one polynomial divided by another? We can. 3 is a polynomial, so is x to the 4th. So after rewriting it, we see, yes, it is a polynomial. Part C looks like it's just a straight polynomial. I think I misspoke. I should have said that, that yes, this guy is a rational function. Okay, part C looks like a straight polynomial, but we've already decided that we can divide anything we want by 1 without changing it. And now it is a polynomial divided by a polynomial, which makes it a rational function. Part D, 2x over e to the x plus 8. This is the first pretender in our list. This is not a polynomial, because polynomials are not allowed to, I misspoke again, that is not a rational function, because rational functions are not allowed to have e's. They're only allowed to be polynomials. They're quotients of polynomials. So no, that is not a rational function. Part E, 1 over x plus 1 over x plus 3. So if you didn't do this before, I'm going to encourage you right now to make this, to combine those two fractions. So pause the video and see if you can fill in that blank and make this one fraction. Okay, so hopefully you were able to combine those two fractions by finding the lowest common denominator. And now that it's written in this form, it's a polynomial divided by another polynomial. That makes it a rational function. Part F. Again, if you didn't rewrite it, I'll ask you to pause the video here and see if you can clean this thing up. And hopefully we see that you can rewrite this as 2x plus 5 over x plus 1, which looks like a poly over a poly, which makes it rational. So lots of rational functions, even though you might have to do some work to recognize it. Next page, number 7. Asymptotes of rational functions are easy to find. We'll consider horizontal asymptotes, end behavior, first. Theorem, let f of x equal p of x over q of x be a rational function. Case 1, if degree of p is greater than degree of q, then f has no horizontal asymptotes. Case 2, if the degree of p is smaller than the degree of q, then y equals 0 is the horizontal asymptote of f. Case 3 is the hard one. If degree of p equals degree of q, then the horizontal asymptote of f is the quotient of the leading coefficients of p and q. So we're going to see all three cases in just a moment. The above theorem says that end behavior of a rational function is determined by the leading terms of the numerator and denominator. Number 8. Let's go back and find the horizontal asymptotes of the rational functions from number 6. So back on the previous page, looking at the rational functions, we're looking for the horizontal asymptotes. So I'm going to make a little column here, horizontal asymptotes for each of these rational functions. Okay, so the first thing we need to look for is the leading, well, we need the degree. So the degree upstairs is 4, degree downstairs is 2. Remember, degree is just the highest power on the x, which is why we had that little thing about only looking at the leading terms. The -1 and the +1 are pretty irrelevant if x is 100 or 1,000 or a trillion. So we ignore everything except the leading terms. In this case, the degree upstairs is bigger than the degree downstairs, and the theorem that we just saw said that in this case there are no horizontal asymptotes. Just looking down here at part D, I'm going to put a not applicable. Part D was not a rational function in the first place. It turns out it does have a horizontal asymptote, and you can explore that one on your own. But we'll move on to part B. In this case, the degree upstairs is 0. There's no x's up there. Downstairs it's 4. So here the degree downstairs is bigger. And anytime that happens, the answer is y equals 0 is the horizontal asymptote. It's just the x-axis, which hopefully makes sense because if you plug in bigger and bigger values of x, you get 3 divided by a million, 3 divided by a billion, 3 divided by a trillion, which is approaching 0. Okay, part E, going vertically here. In this case, the degree upstairs, highest power I see is a 1. Downstairs, you have to, in your mind, distribute, and you'll see that this is x squared plus 3x. Now, all I care about is the leading part, so you can ignore the 3x. You just need to know it's x squared. So upstairs is a power of 1, downstairs is a power of 2. Go back and take a look at what case we're in. hopefully we see the conclusion here is the same as right up above. Y equals 0 is the horizontal asymptote. Part C, the degree upstairs is 3, downstairs is 0. The higher degree is upstairs, which means there are no horizontal asymptotes. And then finally, part F is the tricky one, but it's easy when you know how. In this case, the degree here is 1 and degree here is 1, so it's equal. So what this says is, again, ignore everything except the leading terms. And then when you ignore those, you can cancel these x's here because it's the same, and you just get 2. And it says that kind of in a funny way, but on the next page, it just basically says, look at the quotient of the coefficients. So there's a 1 there, and there's a 2 upstairs, and 2 divided by 1 is your answer. It's just plain 2. And horizontal asymptotes always are of the form y equals. So y equals 2 is our equation for the horizontal asymptote. Number 9, when do vertical asymptotes show up? When the denominator approaches 0 and the numerator does not. 10, let's find the vertical asymptotes of all the functions from number 6. Okay, so we'll make a new column here for vertical asymptotes. Okay, so we're looking for places where the denominator is 0 and the numerator is not. That's what's going to make a function blow up, is when you divide by 0. And we actually saw that for this average cost function. When x was 0, we saw up here that we were dividing by 0, which is a bad thing generally, but it ends up just leading to vertical asymptotes, in this case at x equals 0. So let's take a look at part A. Question is, when is the bottom of this fraction, when is this guy right here equal to 0? So it turns out it never is, at least not in the real numbers. X squared plus 1 is always a positive thing, which means there are no vertical asymptotes. Let's take a look at part D, again making the denominator equal to 0. So hopefully you can just look at that and know that something funny is happening, but even if you can't, you can try solving this equation, and at some point you'll try to find the natural log of -8, which is a problem. It doesn't exist. So again, this guy has no vertical asymptotes because it is also never equal to 0. E to the x plus 8, the denominator, is never 0 because e to the x is always some positive number. And then you're adding 8 more, so it's definitely never 0. Okay, part B, making the bottom equal to 0. Well, that's easy. It just happens at x equals 0. Part E, making the bottom equal to 0. There are 2 of them in this case, x equals 0 and x equals -3. Those are the 2 numbers that make the bottom 0. Those are the 2 vertical asymptotes. And then finally, part F, making the bottom equal to 0. That happens at x equals -1. And just want to highlight that when we're asking for asymptotes, they're always equations, not just numbers. So notice that we were very careful here to put not just -1, but rather x equals -1. Not just 2, but y equals 2. So vertical and horizontal asymptotes, write the equations of vertical and horizontal lines. Okay, on the next page again, 11. What happens if both the numerator and denominator approach 0 at a certain x value? Here's a quick sketch of f of x equals x squared times the quantity x minus 2 divided by x minus 2. So what we're going to do here is essentially just cross off the x minus 2's and say, well, this is really just x squared. So all we're going to do is draw a graph of x squared with one little funny thing that happens. So here's the graph of f of x equals x squared. But if I want to graph the function that's there, which includes those x minus 2's which just vanished, well, it's the same graph. It just looks like x squared, except one little thing goes wrong. What happens if you try plugging in x equals 2? Well, then you have a 0 in the bottom, and we're not allowed to divide by 0. And the fact is that 0 in the bottom essentially cancels with one that's on top, but the way that that appears in the graph is pretty straightforward. All we have to do is go to x equals 2. That's the place where the where we're dividing by 0, and go straight up to the curve, and then right there, we're just going to put an empty hole. So it looks just like y equals x squared with a hole at x equals 2. And if you want to be really precise, you can actually figure out the y coordinate. So how are we going to find the y coordinate? Well, you can't plug x equals 2 in because then you're dividing by 0. So what we'll do instead is plug x equals 2 into the thing that you get when you cancel those guys. So plug x equals 2 into just that function, x squared, and we get 2 squared, which is 4. So the hole happens exactly at the point 2 comma 4. Number 12, what is the significance of zeros of the numerator of a rational function? So we already saw up above that vertical asymptotes show up when the denominator is 0. So now we're asked about when the numerator is 0. So if the numerator is 0, then you've got 0 divided by some other number that doesn't much matter. 0 divided by anything is 0. So these are just x-intercepts, places where the y value is 0. We finished this section by comparing the end behavior of different types of functions. We say that f dominates g if f eventually grows much faster than g, that is to say, if the limit as x approaches infinity of f of x over g of x is infinity. So if the top gets big much faster than the bottom does, then essentially we've got something like, okay, maybe the bottom is big, but the top would be huge. So that's what we're saying when we say that f dominates g, and something huge over something that is only big, the whole thing is still huge. So 14 talks about this thing called the hierarchy of domination, and we'll look at this list, but let's just go to the next page and take a look at an example first. Let's use our guidelines from above to analyze the end behavior of these functions. We can use Geogebra to confirm. So we're just going to write here the limit. So end behavior means as x approaches infinity, and also as x approaches minus infinity. That's end behavior. Okay, so I just copied and pasted that throughout. So let's think about limit as x goes to infinity for this first one, part A. So essentially we're looking at, I'll put an arrow here, it's like the square root of something huge divided by ln of something huge. Square root of something huge is still huge. Ln of something huge is still huge. Both top and bottom go to infinity on their own. So what happens when you divide them? Does the top win out? Does the bottom win out? Or is it essentially a tie and maybe the whole thing just cancels and you get 1? Maybe. So that's what this hierarchy of domination is supposed to help us with, is what do you do when it's an infinity over infinity? And you're just trying to figure out who wins the race. So the functions that we're looking at right now, we've got square root of x, which is a power function, and then we have ln of x. So those are the two things that we want to find in our list on the previous page. Okay, so power functions right here, and log functions right here. So if you have a power function and the p is bigger than 0, then it dominates a logarithmic function. So that means that the thing on top in the previous example, it wins. The power function dominates. It goes to infinity faster than the log function does. So what that means is that we're looking at an example where the bottom is pretty big, it goes to infinity, but the top is huge, it dominates. And something huge divided by something big is still really big. So this thing goes to infinity. Let's take a quick look at that previous guideline a little bit more now. So maybe we were taught in some other class that exponential growth functions, they grow faster than anything you can name, so that's why they're at the top. In the parentheses here, it talks about what to do if you have two different exponential functions in the same example. So if we had maybe 3 to the x divided by this thing right here, what is that, 10 to the 9th billion times 2 to the x. So if x gets really big, you know what happens. That's what this thing in the parentheses is supposed to help us figure out. So a billion on the bottom is a pretty darn big number. But what this thing in the parentheses says is that the higher base dominates the lower one. So the 3 beats the 2. Even though the 2 to the x has a billion sitting in the front of it, even though it's going to win for a little while, eventually the 3 to the x is going to win. The top one dominates, it goes to infinity much faster, and it pulls the whole fraction up to infinity. Okay, next one, we just saw the power functions with p bigger than 0. Any power function where p is bigger than 0 is second. And if you have a tie, like x to the 4th and x cubed, 2 power functions, again, the higher thing wins. So x to the 5th would dominate a billion x cubed eventually. Log functions are next. If you have 2 log functions that are together, like log base 5 of x and log base 4 of x, they actually kind of tie with each other. I'm going to be a little bit coy and not be explicit about what that means, but I would ask you to think about, maybe with the help of your calculator or Geogebra or something, what this limit is. So you can experiment with that later on, but essentially those 2 logs tie each other. Neither one really dominates. Okay, part D. Next ones are constant functions. They're not very strong. And then you have power functions where p is less than 0. So like x to the negative 2. And then finally, an exponential decay function contrasted with the exponential growth function we saw up above. And then there's a note, rational and polynomial functions behave like the power functions by just looking at leading terms. So for example, one of the rational functions we saw on the previous page worked out to be equivalent to this 2x plus 5 over x plus 1. And then we decided that this thing essentially just behaves like the number 2 when x is really big. So if I had to compare this 2x plus 5 over x plus 1 to something else, like x squared, then it would be like comparing 2 to x squared. So it's okay to just look at the leading terms when you have rational or polynomial functions as one of the things you're trying to compare. Okay, so let's go to the next page again and continue working with part A. So we've already done the end behavior to the right. Let's take a look at the end behavior to the left. As x goes to minus infinity, essentially what I'm being asked to calculate here is the square root of minus infinity divided by ln of minus infinity. Okay, both of these are problematic. Neither one exists, at least not in the real numbers. So this equals nothing. I mean, this just doesn't even exist. A more interesting limit that isn't really asked for here, but we're going to consider is the limit as x approaches 0 of this function. And again, I'll put that funny plus sign to say we're only plugging in numbers bigger than 0, so we don't have any problems. We're not doing square root of anything negative. Okay, so let's take a look at what we're really thinking about in this one. Now I'm looking at something like the square root of 0 divided by ln of 0. Okay, square root of 0 is just 0. ln of 0 doesn't exist. But if you plugged in a number that was just a little bit bigger than 0, that's the plus sign, then you'll see on the graph of y equals ln of x that you have perfectly good y values. So here's the graph of y equals ln. And if you send the x's to 0, then you are sending the y's down to minus infinity. So it's like 0 divided by minus infinity, which is really, really 0. And both top and bottom are trying to get you to 0, so you will get to 0 very fast. So the point of all this is that with not too much work, I think we've got some good information about a complex function. Square root of x over ln of x. That's what I'm going to think about graphing here. It's complicated. Square root of x, I know what it looks like. Ln of x, we just drew up above. But when you divide these two functions, dividing functions, that's complicated. But we just got some good information. So first of all, the picture doesn't exist when x goes to negative infinity. Doesn't exist anywhere past x equals 0. We saw that, I didn't fill it in yet, but this limit right here as x approaches 0 is 0. So that means this function is going to approach the origin When x goes to 0, so does y. If you plug in, like we did up above, we saw right here 0 divided by some negative numbers. So the whole thing is going to be negative, which means that it's got to be coming from down there. It's got to be negative. But eventually, it's going up to positive infinity. So at some point, it's got to head up forever. Now, I don't know exactly where that point is, but I know eventually it's got to head up to positive infinity. And if we really wanted to, we could figure out what this intercept is. Here we're looking for the place where the sign changes. Okay, I paused the video there because I knew that this graph didn't look good to me, but it took me a moment to figure out what was going on. There are no other x-intercepts. We saw before that x-intercepts happen when the numerator is 0. The only place that's equal to 0 is at x equals 0. So this graph cannot possibly hit the x-axis a second time, but it does change sign. It has to be negative here in the beginning and then eventually positive infinity. And the way we're going to get around that is not by having an x-intercept, but actually by having a vertical asymptote. So we saw before that vertical asymptotes happen when the bottom of a fraction is 0. So really we're interested in knowing when ln of x is 0. And that happens at x equals 1. So this function actually has a vertical asymptote at x equals 1. So let's start over on this graph. So it's got a vertical asymptote at x equals 1. I know that eventually it has to go up to positive infinity to the right. We saw that. And it has to hit here and be negative. And what does it do in between? Well, it can't hit the x-axis anymore, which I guess means it's got to approach this vertical axis going down. And at some point, it better turn around and approach this vertical axis going up. So this is by far the most complicated graph we have sketched. But with a little bit of analysis, okay, maybe a lot of analysis, I think we've got a pretty darn good idea of what the graph of this very complicated function looks like. So let's pull this up on Geogebra and see if we can get something that, see if it agrees with what we said before. Okay, so the function is f of x equals square root of x divided by ln of x. Okay, that looks pretty good actually. So we can peel this out a little bit and pull this down to see that the vertical asymptote at x equals 1. We decided that it was going to hit the origin and be negative, and then it goes down forever, and then it's positive, and then it looks like it's asymptoting out here, like getting closer and closer to 0. Is that what we said? That's not what we said. So either we made a mistake here or Geogebra is kind of lying to us. But I think that we did the analysis right here. We had something huge over big. Eventually it's got to be huge, even though it might look like the bottom function is winning for a little while. So we're going to drag this to the right, and I think eventually, this thing will hopefully start to head back up. And sometimes it takes a long time before that happens. But in fact, this one is going up to infinity, even though it took a long, long time just to get up to 50. Looks like we're out here at, I don't know, like 500,000. So sometimes, you know, the technology can be deceptive. Oops. And, you know, if you just showed this graph to me, I would be pretty well convinced. Let's see, I think we had it a little bit smushed down. You know, I'd be pretty convinced that this thing, oh, okay, it's getting closer and closer to some horizontal line. And so sometimes it takes a lot of patience to really find what's going on. Technology can be deceptive, and that's why we want to use the math to kind of work with the technology. Okay, taking a look at part B, same idea as before, except this function's upside down. So I guess we can say that same as before, when you try to plug in x going to negative infinity, it doesn't exist. When you plug in positive infinity, essentially what we're saying is that it's the same huge over big that we had before, but here it's upside down. And so if you have a big number divided by a huge number, like 1,000,000 divided by 1,000,000,000, hopefully we see that that is essentially 0. Okay, and then we'll do, I think that's fine. You can graph this function on GeoGebra if you want to get a sense of what it looks like. I'd encourage you to try to make your own rough sketch, just like we did before. It's very complicated to do that, but it's good for you. Let's move on to part C, again, just talking about end behavior. Okay, let's do the second one first, x going to minus infinity. So basically we're looking at minus infinity to the 5th, minus e to the minus infinity. Okay, minus infinity to the 5th is just minus infinity, right? Infinity times infinity times infinity. It's going to be infinity, but it's an odd number of negatives, so the whole thing is negative. Then there's a minus sign. The e to the minus infinity is actually a very nice number, so I'm hoping you pause the video and think about what e to the minus infinity approaches. And hopefully you see that it's 0, which means the whole thing is just minus infinity minus 0 or minus infinity. So eventually this thing goes down and to the left. So without too much analysis, this graph, when you go left forever, goes down forever. And then to the right, when x goes to positive infinity, I'm looking at infinity to the 5th, minus e to the infinity. So that's infinity minus infinity. Both of these things are very big. So the question is, do they just cancel? Is it just 0, infinity minus infinity? Or does one of these infinities win and drag the other one with it? Well, this is where the hierarchy comes in. We have an exponential function and we have a power function, and that's parts A and B, and we know that exponential growth functions beat power functions. So that means that the exponential infinity is much bigger than the ordinary power infinity. And so when you take something big and subtract something huge, you're going to get some negative huge number. And so this one goes to minus infinity, which means as x goes to positive infinity, y goes to minus infinity. So this graph is going to go down on both sides. And it's hard to know exactly what's happening in the middle. I guess you can plug in numbers, like if you plug in x equals 0, I think we get, what, -1, so like it hits this point. It could very well be positive and negative in some combination, but I know that eventually it's going down on both sides. So let's test this one out on GeoGebra real quick. So we'll type in our function. And then we're hoping that it goes down on both sides. And it looks like it's going down here, shoots off the screen for a while over there, and then down here. So I see it hitting the y-axis at -1. We saw that. I'll drag this thing down, see if we can see a little bit more. Bring this thing. So look, it goes pretty high actually before eventually that the e part wins and drags us down to minus infinity. So that's looking pretty good there. It's hard to know exactly what's happening in the medium, in the intermediate spaces, but definitely down and to the right and down and to the left. Calculus will be very useful with figuring out precisely how to know what's happening in the intermediate. Okay, last one is this thing right here. Again, the basic idea when you have a rational function is to just look at the leading terms, only the highest powers. So I'm going to say this is basically the function 3x to the 6th over 7x to the 4th, the whole thing divided by 10x squared. That's legitimate because we're looking at end behavior and we're making x very big. And when x is very big, this x to the 6th is going to completely dwarf 3 times x and subtract 10. So it's okay to just look at the 3x to the 6th. That's the only important thing when x is huge. Okay, and then we can clean this up just a little bit. So I've got 3 sevenths, and there's an x squared up there when I cancel some x's, divided by 10x squared down here. And then you can really cancel those x squareds, and so we just get 3 sevenths over 10, which is 3 70ths. So that means that the limit here, as x goes to infinity, of f of x is 3/70, something close to but not equal to 0. And in fact, the analysis to go to minus infinity is exactly the same. And so the answer is exactly the same. So this thing goes to 3/70 when x approaches infinity and when x approaches minus infinity. And so we can type this one into GeoGebra as well. So f of x equals, all right, lots of parentheses here because the function is quite complicated. In fact, I'll pause the video and just type this thing in. Okay, so I typed it in. We're about to graph it on GeoGebra. We're trying to see that this graph goes to 3/70 at the far right and far left. That's a horizontal asymptote, both directions for the end behavior. So 3/70 is really close to 0, so we're probably going to have to rescale, but let's go ahead and graph it here. Okay, crazy things happening up there. Looks like a vertical asymptote. And another vertical asymptote over here. It'd be kind of tough to figure out exactly where the vertical asymptotes are, but we've talked about vertical asymptotes, so maybe there's some sense as to where they'd come from. But if you go to the far right, it looks like it's getting closer and closer to 0, but actually it's closer and closer to 3/70, and the same thing over here. So maybe let me just type in 3/70 so I can get a decimal. All right, 0.04, that's what 3/70 is. So we're expecting that this graph is approaching not 0, but 0.04. All right, so 0.04 is that number right there. How does it look? Towards the left, it looks like we're going to 0.04. Towards the right, I'm going to drag this in a little bit just to see if it really seems to be approaching this horizontal line at 0.04, both sides. So this is interesting. It actually went above 0.04. Is that okay to cross the horizontal asymptote? It actually is. But now that I realize there's some rounding happening, the horizontal asymptote isn't exactly 0.04. It's just rounded. So up here somewhere is a rounding button. So right now it's going out to 10 decimal, or to 2. But if we make it go out to 10, 0.04286, that's really where this thing is leveling off on both sides. Okay, so there's some stuff about comparing functions. It can be quite involved, quite complicated. That's okay. With practice, it gets easier. The activity is on the next page. It's in your book, but I've also put the 2 problems right here. So this video will end. I'll make a separate video where I go through these, but give it your best shot before looking at the video.